In this lecture, we're going to talk about our next sorting algorithm, Quicksort, another sorting algorithm which is a fast sorting algorithm, as the name suggests. Like merge sort, Quicksort is a divide and conquer algorithm, and the central part of Quicksort that we really have to understand in order to understand how it works is the partition function. Merge sort, remember, took an array, subdivided it into two equal sized parts, and then quick sorted both parts recursively, and then merged the two subarrays into one big array that was sorted. And so the core algorithm behind merge sort was the merge algorithm. The core algorithm here, again, is partitioning. So let's look first at partitioning. Okay. The goal of partitioning, the partition algorithm, is to divide an array. It could be the entire array or just a subportion of that array, because this is a recursive algorithm, into parts left, which we'll call left and right. And it should have the property that after the partition is done, everything in the left portion is less than or equal to everything in the right portion. Now notice I said everything in the left portion is less than or equal to everything in the right portion, but I didn't say anything about what to do about things within those two regions. So within those two regions, they might be out of order, and that's okay. Because we're going to recursively solve that problem. But here's an example for what partition looks like. If the input to our partition algorithm looked like this, an array of length 8 with values 5, 7, 9, 6, 0, 9, 5, 3, then if we ran the partition algorithm, a valid running of the partition algorithm on this might look like the following. If the pivot value, which we'll talk about in a minute, is 5, then we see that there's a left portion, which I'm highlighting here, 350, and everything in that region is less than or equal to 5, which is our pivot. And you'll notice that the right portion is 69975. Everything there is greater than or equal to the pivot. The pivot is the value that we use to separate the two halves, or the two parts, let's say. So there are a few things to notice here about this result. The first thing to notice is that these two parts, left and right, are not necessarily equally sized. We have 3 things on the left and 5 things on the right. It would be ideal if they were equally sized, but it's not always going to be the case. The second thing to notice is that the pivot value, which is used to divide the two portions, could appear on either side, left or right. So in other words, you see that there is a 5 on the left and a 5 on the right, and that's okay. Okay, so those are a couple things to notice about the partition algorithm. The partition algorithm is a bit tricky to implement. In fact, I spent quite a bit of time preparing for this lecture trying to get it just right, but also understandable. I've written this algorithm a handful of times, and every time it takes me a while to get it right. The input to the partition algorithm, and this is the version. There are different partition algorithms. This is Hoare's algorithm. Hoare is the one who Tony Hoare is the one who wrote the original Quicksort. Okay, he developed Quicksort, and the basics of Hoare's partition algorithm is we're given a few things. First is the array, then the left and right bounds of the array. That's the region of that array that we're trying to partition. It might be the entire array, but it might just be a subportion of that array. And lastly, I've added here the pivot index, and that's an index between left and right inclusive that holds the value that we consider the pivot. Now, again, the pivot is the value that is going to divide the left and right portions. Everything less than or equal to the pivot will be on the left. Everything greater than or equal to the pivot will be on the right. And the pivot, if it appears, it could appear on the left or the right, or both, if there are multiple values that are equal to the pivot. Okay, so how do we know what that pivot index is? Well, it's any valid index between left and right, and we'll talk more about what that is in a bit. But here we'll assume that it's given. Okay, the basic idea behind partitioning is we're going to take this array that we've been given, and we're going to walk from the beginning forward until we find something that is out of place with respect to the pivot. So at the beginning, the left portion of the array, we should have all values that are less than or equal to the pivot. So if we find something greater than the pivot or equal to the pivot, then we will stop at that location. And then we'll have a second index that will walk from the back of that subarray towards the beginning and stop if it sees something less than or equal to the pivot. And once we find something greater than or equal to the pivot and less than or equal to the pivot, we can stop and swap those two values, and then we can continue our march inward towards each other. So the first thing we do is we're going to say, we're going to have two counters, I and j, which begin just before and just after the left and right values, respectively. So notice that these are starting with initial values that are actually outside the bounds of what we're trying to partition. That's okay, and you'll see why. Here's our pivot value, which is just whatever index, the value at the index that we were given. While I and j haven't crossed, they're going to be marching forward. So I is marching from the left, j is marching from the right. We're going to have these two loops inside. This is the loop that marches I forward. And the next one is the loop that marches j backwards. Okay, and there's a lot going on here in these two loops. Notice several things. First of all, these are sort of standalone while loops. Notice the semicolon after the closing parenthesis in both cases. So there's no body to this loop. The only thing that's going on is we're going to say, while this condition holds, keep executing. And what does that condition do? Well, the first thing that it does, the very first thing, is it actually increments I. And that's why it's okay that I actually started one before the left, because the first thing that we do is we march one forward to the left value. And it's the same thing with j. It starts one past the right because the first thing we're going to do is march backwards to where the right began. And while the value at array sub I is less than the pivot, then we're going to keep marching forward. And after we finish that, while the jth entry is greater than the pivot, we're going to keep marching forward. So we march forward until we get to something equal to or less than equal to or greater than the pivot on the left, and equal to or less than the pivot on the right. Then, if I and j have not met or crossed each other, then we swap these. Okay, we swap those two items, and then in the next next time around, we're going to continue until they meet or cross each other. Once this is all done, we're going to return j. And the reason we have to return something is because we don't know where these two I and j are going to meet. When they're done, though, j will be at the position that is the end of the left portion. Okay, and that's important to keep in mind, and that's actually one of the trickiest parts for me to remember. So this is the partition implementation, and this is a working implementation if you care to code it up. Okay, so now that we have the partition, actually, let's do some analysis. Okay, how much time does it take to partition an array of length n? Well, it's pretty clear that we're going to march forward and backwards until they meet, and each element of the array is going to be visited exactly once. So it's fairly clear that for an array of length n, this is order n. Okay, this is an order n algorithm. One other thing that I want to point out, because we're going to come back to this later, is that notice that these two loops stop when they reach something equal to the pivot as well. So for example, if the I index reaches something that's equal to the pivot and the j index reaches something that's equal to the pivot, what's going to happen? They're both going to stop and then swap their values, which seems silly because you're swapping two values that might even be equal to each other, and they could go in either left or right. But we'll see later why this is actually a good idea to stop at the pivot value and not just values greater than or less than the pivot. Okay. All right, so now that we understand the partition algorithm, which is the core of the Quicksort algorithm, we can go over the details of Quicksort itself. At a high level, the recursive algorithm proceeds in this way. The first thing to do is to choose a pivot. And in our case, we're actually choosing a pivot index somewhere between left and right that we want to use as the pivot value. Okay. Then we're going to call the partition algorithm, and that partition algorithm splits it into two subarrays of some lengths. Okay. And we find out where that split occurred after partition is done. And then on those two, left and right, we recursively quicksort both of those. And that's it. That's the algorithm. So here's a quick and dirty implementation of that also, I believe, should work. I haven't actually run this code, but I think it should work. We have our base case here. We only want to proceed if left is less than right. And if left is less than right, then we have an array of length at least 2, because left and right are the inclusive endpoints of our subarray. And if left is equal to right, then we have a subarray of length 1, which, as you know, as I've promised you, is already sorted. The first thing that we do then, if we are not in the base case, if we have something to sort, then if we have a subarray of length 2 or more, then we have to choose our pivot, and how we choose our pivot is to be determined. We'll talk more about that later. Okay, so this is sort of a to be determined function. Then we call the partition algorithm that we just discussed, and that returns to us the left end, the end of the left portion of the array. So then we recursively call quicksort, call this function itself on the left portion and the right portion, and that's it. Okay, so let's talk about the analysis of this algorithm. There's an important part that we have left out, and that's this to be determined part that I talked about earlier. How do we choose the pivot? Well, what should it be? Well, if the pivot is really well chosen, then what will happen is that when we partition an array, it will end up with roughly equal sized subarrays. And that's important, okay? So I want to show you what this looks like. Okay, this is sort of the best case. If we have originally an array of length n, so here's our array of length n, we're going to partition it, and in the best case, our pivot value allows us to partition into exactly equal length subarrays of n over 2 and n over 2. And then we recurse on the left portion. And when we recurse on the left portion, it's going to be partitioned into equal size subarrays of n over 4 and n over 4. And similarly, when we recurse from here down to here, it's going to this one is going to be partitioned into n over 4 and n over 4 and so on. So in other words, the best case analysis is that every time we pick the pivot, we somehow manage to partition our array exactly in half. This isn't realistic, but it's a best case scenario, okay? And this continues all the way from the first level of the recursion, all the way down to the second level of recursion, third level of recursion, and so on. And notice, this is the entirety of everything that's happening, right? But this is not all of this is happening at once, because this is a recursive algorithm. So we would, sort of trace maybe down to here, and then we come back up here, and then we go down here, and then back up here, and then here, 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 right? So this is a tree that we would only be doing one of these at one time, okay? So what's the total amount of work that happens if we were able to pick the pivot in such a way that every time we partition exactly in half? Well, we know that the partition algorithm costs n for an length n array. So at the top level, we would have to partition, and it would cost us n for this entire array. Then for this length n over 2 array, it would cost us length n over 2. And for this length n over 2 array, the same, n over 2, and we have 2 of them. So the total cost for this level of the recursion, which is 2 function calls, is n. So over both function calls, we have a total amount of n work that we have to do due to the partition algorithm. And then similarly, we have n over 4 work to do in each of these 4 subarrays, so the total is n. And if we keep going, you'll notice that each time we have order n work to do, and this keeps going all the way down until we get to subarrays. There are n subarrays of length 1. okay? And that also costs us n, okay? There we go. So the question is, how much is all of this going to cost us? We have n plus n plus n plus n plus n plus n, and so on. How many n's are there? Well, the real question then is, how many recursion levels can we go before we get down to a size 1 array? And the answer, of course, is we can only go down log n recursion levels, because every time we're dividing in 2 the size of the subarray, okay? So the overall runtime is we have this factor of n, and we have log n of those. So we have that in the best case, this is n times log of n. Okay, so that's where we get our best case analysis for Quicksort. But again, this is if we pick the pivot such that each time we partition, we get equal size subarrays. Okay, so this is big O of n log n. It's also big omega of n log n. So let's go ahead and fill in our table. We have Quicksort is going to be big O of n log n. Okay, at least that's what it seems like in the best case. But the question is, another question is, what if the pivot was poorly chosen? What do we mean poorly chosen? Well, we mean that maybe it didn't divide the subarrays into size 1/2 and 1/2 of the original. What if it divided it into, say, most of the array ended up in the left portion and only a small amount in the right portion, or vice versa? How could this happen? Well, suppose that your pivot picking strategy was something like the following. You were given the following array: 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and your pivot picking strategy was always pick the first index as the pivot. If you do that, then the first time you partition this, you're going to partition it into a subarray with all values less than or equal to 1 and all values greater than or equal to 1. So what does that leave you with? Well, that's going to subdivide this into essentially this left and right portion. So the left portion is 1, and the right portion is everything less remaining. Then if you continue with this, if you recurse on the right portion, what are you going to do? You're going to pick 2 as your pivot value. And that's going to subdivide the array. Subdivide which array? This array into 2 on the left and everything remaining on the right. Okay? And then if you're going to use 3 as your pivot, you're going to subdivide this array into 3 on the left and everything remaining on the right. So what's the running time of that? Well, every time you do that, you're incurring a cost of order length of the array for the partition. But that length of that partition is not going down by a factor of 2 every time. It's going down by just 1 every time. So this is going to be n for the first partition plus n minus 1 for the second partition. What do I mean the second partition? I mean everything that remained after we cut out that first one, plus n minus 2 for this third partition, right? Plus n minus 3 plus n minus 4 plus ... plus 1. And what is the sum of numbers from 1 to n? Well, this is big O of n squared. So therein lies a bit of a mystery. Is Quicksort n log n, or is it an n squared algorithm? And if it's an n squared algorithm, why do we call it Quicksort? Well, it is an n squared algorithm if you do a poor job of picking the pivot. And the poor job of picking the pivot would be a deterministic strategy, like always picking the first element. Because as I just showed you, if you give Quicksort a sorted array and you always pick the first element as the pivot value, you're going to get an n squared running time. Similarly, if you always pick the last value as the pivot, you're going to get n squared running time. Okay, and even if you pick like the middle element, you can still construct arrays, not as easily, but you can still construct arrays that will have n squared running time. Okay, but there are ways to combat this. Okay, so what we'll say is this is n squared if the pivot is poorly chosen for the reasons that we discussed. But we can most of the time avoid that. Okay, so the question is, if we want to pick the pivot well, such that it results in a good running time, which value do we want? Okay, which value do you want? Well, you might say that you want the average, but it's not the average that you want, because if you consider arrays that have very skewed distributions, the average itself can be very skewed. So what you actually want is you want the median. And what is the median of the array? Well, a simple way to find the median of the array is to sort the array and take the middle element. But that's kind of begging the question that we're already trying to solve, or presupposing that we've already solved the sorting problem. So finding the median is almost as hard as sorting the array itself. So the median would be good, but we don't know how to find it terribly efficiently. But a good there are some other deterministic policies and non-deterministic policies that work pretty well. A non-deterministic or a random policy is actually a pretty good one. If this is your subarray and you have to pick some pivot value between the left end and the right end, just pick it randomly. Now, yes, this could result in some bad pivot choices from time to time, and maybe every so often it'll be a very bad pivot, but on average, you're going to do very well, okay? Doing the analysis for this is a bit more than I would like to take the time to deal with right now, but actually picking a random value, or rather a random pivot index, is actually a pretty good strategy. The only downside to it, really, is that generating good random numbers can be expensive. So it's better to go with a deterministic strategy if we can. And your book, the book that we're using, suggests the median of 3 as the pivot. And that's where you take the left end, that index, which is a bad idea by itself, the right end, which also is a bad idea by itself, and the middle element, which is also a bad idea by itself. But you take those 3 elements and you pick the median of those, which you can compute in deterministic time, or in a fixed amount of time, rather, and very quickly, and choose the median of those 3 as the pivot. And the upside to this is it's fast, it's very good on average, and it's really hard to combat. It would be hard to construct an array that can cause this to have bad runtime behavior. So that's a pretty good strategy, median of 3. All right, now I want to talk about a couple more things. Okay, actually, let's finish our analysis before. This is also big omega of n log n. Okay, there's no real early exit for Quicksort if the data is already sorted, because we have all these recursive calls. Is it a stable sorting algorithm? Well, no, it's not. And that should be fairly obvious by the fact that when we partition, we're moving left and right towards each other, and we can take equal values and swap them, which we talked about earlier. So this is not a stable algorithm, but it is an in-place sorting algorithm, which makes it slightly better in that respect than merge sort. Okay, so it is a memory efficient sorting algorithm. And that's one of the reasons why it's very fast. Now let's return to this question that I talked about earlier about partitioning values equal to the pivot. When we're partitioning, we would stop the left pointer, left index, if it gets to something that's greater than or equal to the pivot, and the right index if it gets to something that's less than or equal to the pivot value. And why do we stop at the pivot value itself? If the pivot value can still live in the left portion, why not leave it there and just pass it by? And if the same thing on the right portion, why not just pass it by until we get something strictly greater than the pivot or strictly less than the pivot on the left and the right, respectively? Well, the reason is runtime, actually. Okay, suppose that you have a very long array that looks like this. Okay, we have a very long sequence of 4s. Okay, what would happen? Well, first of all, which pivot value should you choose for this long array of 4s? Well, obviously, you would choose any of them, and your answer would always be 4. Now, what's going to happen to our partition algorithm, if we start our 2 pointers here and here, okay? So here's I. Actually, let's just label this I and J, okay? The first thing that's going to happen is that I is going to march forward until it gets to, and here's the thing. If we stop at the pivot, then I is going to stop here, and then J is going to back up until it stops here. And then what happens? We swap 4 and 4, okay? Then I marches forward, J marches back, and we swap those 4s. Then I marches forward, J marches back, and we swap those 4s, and so on. So everything is getting swapped towards the middle. And that seems silly, and it is a little silly. But watch what happens if we didn't behave that way, okay? So let's rewind. Suppose that I didn't stop when it got to something equal to the pivot, only something greater than the pivot, okay? Then we would proceed all the way to the end of the array. And once we got there, okay, and they meet, and we'd have to protect against this as well. Guess what happened? We now have an imbalanced partition, right? If we swapped as we went, which is what the correct algorithm does, then I and J would meet somewhere around here, and we would have a roughly equal or an equal partition. And that's what we want for good run times of the quicksort algorithm. But if we didn't stop at the part and swap for the pivot values, then I would proceed all the way to the end, and then we would have an imbalanced partition. Okay, so it's actually a runtime issue is the reason why we stop at the pivot value. Now, you might think this example is very contrived. In other words, why would I be sorting a very long array of 4s? And I'm not suggesting that you should sort very long arrays of 4s, but think about the following. Suppose that you had an array of length 1 billion, and all of the values in that array had value between 0 and 100. So you have a length billion array, all values between 0 and 100. What do you have a lot of in there? Well, you have a lot of duplicate values in there. As you're quick sorting this from a billion down to smaller subarrays, at some point as you go down your recursion, you're going to get to regions of the array that have a lot of 4s in them, or a lot of 10s in them, or a lot of 50s in them. In other words, you're going to be grouping these things into tighter and tighter groups, and you will end up with subarrays that have all the same value. So if there are a lot of duplicates in your starting array, at some point you're going to end up with a subarray that has a lot of duplicates in it. And if you don't stop at the pivot value, then at least for those subarrays, you're going to degrade, this algorithm will degrade to order n squared instead of n log n performance. Okay? All right, so the last thing that I want to talk about is and actually, before we leave this, let's return back to the analysis of quicksort. Would I call quicksort an n squared algorithm? No, I would not. It's only n squared when you pick the pivot poorly, and you kind of have to almost purposefully do that because everyone knows you need to have a good strategy for picking the pivot. So this really is an n log n algorithm. It has n squared worst case performance, but I would say as long as you're picking the pivot carefully, this is n log n. Okay. Now, this last topic is one of practical importance, function call overhead. Recursion, this is a recursive algorithm, and recursion is an expensive thing to do, especially if you don't have a good compiler or way of compiling out the recursion. Sometimes you can compile out recursion into tail call recursive structures that can become loops. But in this case, that is hard to do because you have 2 recursive calls. Okay. Function calls are expensive. Expensive things slow down our algorithms. So how could we make quicksort faster? Possibly by reducing the number of function calls. And we're making many function calls, one for each subarray. And the most that we're making actually is on all these length 1, 2, 3 arrays down at the very bottom of our recursion, right? At the top, we make 1 recursive call for the entire array, and then 2, and then 4, 4, and then 8, and then 16. But most of those recursive calls are for these tiny little subarrays down at the bottom, okay? So here's an idea. Each recursive call to quicksort that we make needs to sort its portion, just its portion. And as long as it sorts that portion, everything else is fine. So why do we need to use the same algorithm for every level of the recursion? Maybe at the lowest levels of the recursion, we could use a non-recursive in-place algorithm, okay, such as insertion sort. Okay, so this is a bit of a bizarre idea. Here we have quicksort, which is an n log n algorithm. And I'm suggesting that when we get down to the lowest levels of the recursion, we replace quicksort for those small subarrays with insertion sort. And you might say, but insertion sort is order n squared. Why would we want to augment an n log n algorithm with an n squared algorithm? How would that be of any benefit? Well, again, it's because there's no recursion in insertion sort. Okay, so I want to show you the results of an experiment I ran where the structure is basically the following. Run quicksort as long as the left and right portion or the subarray is long enough. Say, the subarray is of length 100 or 50 or something like that. But if the length of the subarray gets too small, then just run insertion sort on just that portion. Okay. And you can change how long that threshold is, right? You can say, well, I'll run insertion sort on very small arrays versus running it on very large arrays. Okay. Here are the results of doing that. Okay. Let me pull up my markup here. Okay. So what I did here was I did an experiment where I had an array of length, the n was 10,000, okay? And I did this experiment 1,000 times just to get average running times, as total running times rather. The running time here is measured in seconds, and the x-axis here is the threshold for insertion sort. So in other words, how long or how large did that subarray have to be before I called insertion sort? All right, now this right here is about 1.58 or something. Oops, stop. Okay, so the timing for this portion, or just this is quicksort by itself, it's about 1.58 something. Okay, that's this marker right here. And how do I know that's quicksort by itself? Okay, how do I know that's quicksort by itself? Well, because down here, that's where the threshold for insertion sort was 0. In other words, only for length 0 arrays did I use insertion sort. In other words, never use insertion sort. Over here, if I use insertion sort for, length 400 arrays or length 100 arrays, and then the resulting timings are given here and here. And what do you notice? Well, insertion sort, as you use it for larger subarrays, the running time actually decreases. Stop. Gotta love technology. All right. The running time actually decreases along this curve until we get to a minimum down here of, I think that was about, it looks like about 1.4. And then it increases again. Now, why does it go down? Because, and this minimum, by the way, this was about 30. Okay, that point right there was about 30. It goes down because we're making, the further we go to the right, the fewer recursive calls we're making because we're using insertion sort for greater and greater subarrays. And with fewer recursive calls, there's less cost attributed to those recursive calls. But why does it start going back up again? Well, because insertion sort is an n-squared algorithm. And so at some point, that n-squared starts to dominate the running time of Quicksort and gets larger and larger. And if you were to continue this, if you just ran insertion sort by itself on all of these experiments, then you get a time of something like 52 seconds or something like that. So really, really slow. So if you ran this experiment just using insertion sort, no quicksort at all, it's like 52 seconds. Quicksort by itself is much, much faster, but you can combine these two and get something that's even faster. And that's kind of the interesting, perhaps not intuitive at first part, is that you're using a slow algorithm to benefit a fast algorithm. But again, Quicksort is fast for large arrays, but it's slow for small arrays because of these function calls. Insertion sort is slow for large arrays, but it's fast for small arrays because n is small. Okay, so this is the kind of non-intuitive result that you can get. You can combine two sorting algorithms and get something better than either one of them. So that's it. Give Quicksort a try, study up, and we'll talk to you next time about more sorting algorithms.